Thanks to the organizers for having me. As you can see, I've changed the title from what was posted for last year because, of course, a year has elapsed and have made progress. Pushed the no preferred reference frame from Bell state entanglement all the way down to the foundation of quantum mechanics. A couple of warnings are in order before I even start. No preferred reference frame, also known as the relativity principle, simply states the laws of physics must be the same in all inertial reference frames. Does not say the laws of classical physics must be the same. It's all physics. And also, you don't want to conflate the relativity principle with the theory of relativity. Newtonian mechanics has the relativity principle and its foundation as well, and it is clearly non-relativistic. So, there's no reason a priori to reject the relativity principle at the foundation of non-relativistic quantum mechanics. With that out of the way, let's look at the argument that I'm going to present here. Really comes from the axiomatic reconstructions of quantum mechanics from information-theoretic principles. And the first thing that we note from those is that the key difference between the quantum and the classical probability theories is continuous reversibility. I'll explain that in the context of pure states and mixed states shortly. So what it will show is that this principle, the very foundation for qubits, the basis of all of the denumerable dimensional Hilbert space structure of quantum mechanics, actually entails the relativity principle applied to the invariant measurement of Planck's constant h. When you look at Stern-Gerlach spin measurements, this is an exact analogy to the relativity principle as it pertains to the invariant measurement of the speed of light c for special relativity. So what essentially the quantum information theorists have done is they've extended Einstein's use of NPRF from boost invariance measurements of c to include SO3 invariance of measurements of h between different reference frames of mutually complementary spin measurements. So what constitutes a mystery about the Bell states is its average-only conservation. And of course, that's responsible for your Tierlson bound. Now you can understand that that results from conservation per information invariance and continuity between different reference frames of mutually complementary measurements. And this maps to NPRF in spacetime. So these axiomatic reconstructions of quantum have succeeded in producing a principal account of QM that is every bit as robust as the postulates of special relativity. So essentially, we have NPRF at the foundation applied to the measurement of Planck's constant, giving you the qubit Hilbert space structure, the kinematics of QM. So when Stern and Gerlach take their magnets and rotate them, they see no change in the deflection pattern of atoms. This is exactly like taking NPRF, applying it to the measurement of the speed of light c to get the Minkowski spacetime for special relativity, the kinematics of special relativity. As Michelson and Morley rotate their interferometer, they see no change in the interference pattern. Here are your references and the book, of course. So, here's a quick outline. Physicists are trying to account for the success of quantum, just like they did for the Lorentz transformations in the late 19th century. There, the M4 Minkowski spacetime at the foundation of SR is based on the boost invariance of C. In other words, you have NPRF plus C. So you have to look at first principal versus constructive explanation. Are you going to be happy with a principal explanation like we have for special relativity? So the quantum information theorist said, well, most people are, of course, happy with principal explanation of special relativity. So that would be great if we could have something like that, right, for your Hilbert space of QM. And that's what we're going to show you here. They have that, information invariance and continuity, at the very bottom. Continuity, like I said, distinguishes uniquely between the quantum and classical probability theories and the entirety of the denumerable dimensional quantum mechanics built in composite fashion from this qubit structure. So what we're going to show in here is that this information invariance and continuity entails the SO3 invariance measurements of Planck's constant h. In other words, NPRF plus h. And this leads to average-only projection, and average-only projection leads to average-only conservation for the Bell states, and that resolves your mystery of entanglement per conservation, according to the relativity principle. So, Fuchs writes, where present-day quantum foundation studies have stagnated in the stream of history is not so unlike where the physics of length contraction, time dilation stood before Einstein's 1905 paper on special relativity. And in that situation, as noted here by Moylan, Maxwell's equations weren't preserved on the Galilean transformations. Most of the Maxwellian physicists at the time were ready to abandon the relativity motion principle and adopt a distinguished frame, that of the luminescence ether. That's what they were. In fact, Einstein, Norton notes that even Einstein was willing to that. He looked into that too, right? But he gave up. It didn't work. And he writes later, by and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results. So, all undergraduate physics majors are shown how time dilation, length contraction, relativity of simultaneity for Minkowski spacetime follow from the light postulate, right? And we can understand the light postulate to follow from the relativity principle. In other words, if there was only one frame that you were able to measure, C, from Maxwell's equations, the value that it has, then that would clearly be a preferred reference frame. So Einstein just said, look, the Galilean relativity is the laws of mechanics must be the same. Einstein said, no, that's the laws of physics, all of physics, to include Maxwell's equations, and therefore everybody has to measure the same value for C. And there's your light postulate. And all of its consequences, right? This is a famous quote about what the difference is between principal theories and constructive theories. So he points out constructive theories are like kinetic theory of gases. And there you're going to have causal mechanisms between objects like molecules, particles, forces interacting to explain things. And principal theories, rather, you're just going to talk about the mathematical consequence of empirically discovered facts. Okay? So special relativity is a principal theory. And today, we have like thermodynamics here as an example of a principal theory, and it has a constructive counterpart, kinetic theory of gases. But yet today, we don't have any consensus constructive counterpart to special relativity. There are some people who still propose theories of the ether, but for the most part, physicists have let that slide. Now, there are, of course, famously people like Brown who object to, principal explanation in the absence of constructive counterpart. But again, by and large, physicists don't worry about it. There's no talk anymore about special relativity doesn't have any constructive counterpart. There's no interpretation for special relativity. All the physics textbooks say, hey, here are the principles of relativity, here are the consequences, and everybody seems to be quite happy about that. So, Hardy says, man, can we do that with quantum mechanics? I mean, quantum theory isn't really principle at this point, nor constructive. It's like an operational theory. We have the axioms, we have the rules, and we use them and they work. But wouldn't it be nice if we could find, some explanation for where this structure comes from? Just like Einstein's principles, right? Special relativity. Fuchs says the same thing. Compare quantum to special relativity. There we have these nice, clear physical principles. But it'd be nice if quantum mechanics could likewise have some nice, clear physical principles, not just some mathematical facts that explain everything. And they have sought, amongst others, to construct quantum mechanics in terms of information-theoretic principles. Here's just a sampling of those from a paper I cited at the beginning. Now, the information theorists, they're excited about these derivations. Here's a quote from Mueller. Can quantum theory be derived from simple principles like Lorentz transformations from the relativity principle and light postulate? And he says, yes, there is. In fact, we can get everything, the wave function, the operators, complex numbers, unitary transformations, uncertainty relations, the Schrodinger equation, tierless and bound. We can get all that stuff from these principles. So why isn't everybody all excited? Why don't we hear this talk, more pervasive in the foundations community? Well, here, like Van Kamp points out, you're just pointing out pure mathematics again. I mean, your information theoretic principles are just really, since they're not related directly to things in space and time, but to information, it's still just a reorganization of the mathematical structure in a sense, right? So we're not totally happy with what you've produced. So what I want to show you is there's reason to be happy. There's reason for their excitement. All you have to do is take one of their principles and show that it entails something very interesting and not totally analogous, special relativity. And that is, it has NPRF extended to the measurement of Planck's constant h. That's what it entails. Watch. As Weinberg points out, when you measure electron spin via Stern-Gerlach magnets, you are measuring Planck's constant h. And as you rotate these in space, you always get the up-down deflection, right? Nothing in between. This is an empirically discovered fact. So we can explain that fact by NPRF, and that comes from their information invariance and continuity as follows. Look at the difference between a classical bit and a qubit, right? In the classical bit, you go from your pure states through only mixed states. But in a qubit, you go from all your pure states are on the surface of your Bloch sphere, which I've put embedded here in real space, and you're always transforming in between them through other pure states. That is uniquely quantum over the classical. And here are your complementary measurements, spin x, y, and z to correspond to your x, y, z axes in real space. So, this continuous reversibility, in other words, you go through pure states to get to pure states. Kobrenitzky and Mueller point out, hey, this is the postulate that comes closest to being a candidate for the genuinely physical kernel of quantum reality. This is very different. He said, if you only know classical information theory, this is as shocking to you as if you didn't know anything about relativity and you heard about the light postulate. So, the information theoretic principle that I'm going to refer to is really a combination of these two principles, existence of an information unit and continuous reversibility. So it's information invariance and continuity. The total information of one bit is invariant under a continuous change between different complete sets of mutually complementary measurements. That's going to be these different sets of mutually complementary measurements. That's going to correspond to your reference frames, and the relationship between them then, of course, is going to be SO3. So here's an example. Suppose we send a state in here and select out our spin up, say in the z direction, and then we do a subsequent SG measurement at direction b hat theta with respect to z hat, right? And here are your two reference frames related to each other by SO3, shown here. The b hat frame and the original frame, the state you produced it in. And you can see that you're always going to get, back here, you get this orientation in this new frame, you're still always going to get, plus or minus 1, just like you did at the original frame. Now, why is that mysterious? Well, of course, your classical constructive model would say, look, you've got these little dipoles coming through here. You selected out for the ones that were only going to be deflected up, and then you did a subsequent measurement on these guys at some other angle. You should have gotten all these different possible deflections out of that, right? As you orient your magnets, rotate them. On these, you should be getting, less and less deflection. But nope, you still always get up and down. So if you looked at the situation, you would say, look, here's the amount of deflection you should get in direction B, given that your initial state was, plus 1 z hat. In other words, you should be getting this cosine theta. Now, because you do have to get plus or minus 1 all the time, plus or minus 1 can average to cosine theta. And that, along with the normalization condition, gives you exactly your qubit structure, right? So you see that this information invariance and continuity leads to the NPRF plus H, an average-only projection. And that's exactly your qubit Hilbert space structure. And all of your denumerable dimensional Hilbert space structure for quantum mechanics is based on this qubit, right? So now let's take a couple of them and entangle them. Here's your singlet, your triplet states. Again, we have Alice and Bob making their measurements at A hat and B hat on the tangled particles. Here are your SU2 symmetries for your singlet state, and then each of the triplet states. You can see the triplet states go by A hat dot B hat in the symmetry plane. So here's your symmetry plane. It would be XY for this state, YZ for this one, XZ for this one. And so you see how you have rotational variance in the symmetry plane, each of the symmetry planes for a triplet state. according to its SU2 symmetry. For the singlet state, it's any and all planes. So let's look at a triplet state. Let's take a collection of data and look at the correlation function. So this is some arbitrary collection of outcomes, +1, -1 for Alice and Bob. And you're averaging them. That's the correlation. Alice at alpha and Bob at beta. And let's organize them according to Alice's equivalence relationship, her +1 and -1 results. And you see what we need to compute the correlation function. We need to know what Bob averages for her +1 and what does Bob average for her -1 results. Well, again, we know that if Bob had measured the same direction as Alice, he would have got +1. Now he's measuring off at some angle b hat, so he should be getting this cosine theta, right? Well, he can't. He always has to get +1 or -1, right? That's your no preferred reference frame. So just like the single particle case, Bob can only obtain this cosine theta on average right here. And then the rest of your probability, your joint probability table with the symmetries implied by NPRF. And you can solve those equations and get your joint probabilities exactly per quantum mechanics. Take those and get your average then for Bob in the negative states, or her +1, and you recover your cosine theta, right? So you see that you have your information invariance does give you your NPRF plus H, which gives you your average-only projection, which gives you now average-only conservation between different reference frames, right? So this mystery of entanglement is this average-only conservation, and it results from conservation per the relativity principle, or more generally, per information invariance and continuity. Here's a picture, for example, and theta is 60 degrees. Here are Bob's outcomes, etc., averaging +1, averaging to a half. And it looks here in the average, it just maps beautifully, right, to what you would expect from your classical constructive picture. But keep in mind, again, that on trial-by-trial basis, Bob is always measuring +1 or -1. So suppose his is supposed to be getting 0. He's at 90 degrees relative to Alice, but he's getting +1 or -1. Alice would say, Bob, your data is crap. It's as bad as it can possibly be. Instead of getting 0, you're getting the extremes, +1 and -1, right? But now, of course, Bob can also partition the data according to his equivalence relation, his +1 and -1 outcomes, and he's going to point to Alice and say, no, Alice, it's your +1 and -1 outcomes that are so horrible all the time. They're not fitting. Notice the analogy we have here to the relativity of simultaneity and special relativity. There, Alice partitioned space-time per her surfaces of simultaneity, her equivalence relation, and according to her partition, it's Bob's meter sticks that are short and his clock's running slow. But Bob can partition space-time, M4, in exactly the same way according to his surfaces of simultaneity, and then it's Alice's meter sticks and clocks that aren't working properly, right? So you can see the analogy with special relativity. It's exact. It's not sort of like, it is that way. It's exactly the same, right? This is a quote from Bell. This was a statement he made. He was answering questions and someone recorded him in a talk in January of 1990. He passed in April of that year, so this was very close to the end of his life. And so he said, I think the problems and puzzles that we're dealing with here, obviously he's talking about entanglement, right? Will be cleared up. Our descendants will look back at us with the same kind of superiority as we are now tempted to feel when we look back at people in the late 19th century who worried about the ether. Michelson, Morley, the puzzle seemed insoluble to them. And then came Einstein in 1905, and now everybody learns it and feels superior to those old guys. It's my feeling that this action at a distance and no action at a distance business will go the same way. Someone's going to come up with an answer, a reasonable way of looking at these things. And if we're lucky, it will be some big new development, like the theory of relativity. In fact, the axiomatic reconstructions of QM, based on information-theoretic principles, reveal a big new development, at least in our understanding of quantum mechanics, right? We see now the relativity principle at work at the foundation of QM exactly is the way it exists at the foundation of SR, demanding the invariant measurement of a fundamental constant in nature.